Hello again. Towards the end of my Starlink talk, I said that very large stars could collapse into a black hole, and that I would talk about them later. Well, we reached my last talk, so we're going to discuss them now. Listening to this lecture, you may at first think that I've got you to watch it under false pretences, and that really I'm talking about the history of radio astronomy. But the observational history of black holes is bound up with radio astronomy, so bear with me, we'll get there. Not of course there's anything wrong with talking about the history of radio astronomy. I was, after all, a radio astronomer. So, black holes. Some history. In the years following the Second World War, there was a lot of surplus ex-military radio and radar kit available. Some of this found its way into Bernard Lovell's hands at the University of Manchester and Martin Ryle's at Cambridge, when it got turned to more peaceful purposes than it had been. Lovell was interested in using it to try and detect cosmic rays, that's high-energy particles travelling through the Earth's atmosphere but originating somewhere out in space. He didn't detect these, though he did detect meteors. Now by this stage the equipment had been moved out to a field borrowed from the botany department at a place called Jodrell Bank, about 20 miles south of Manchester, and it was there because in the city there was too much interference from the trams. It was in ways like this that radio astronomy got started in the UK. In the early days, and this picture was taken in 1947 at Jodrell Bank, it was apparent that there were a number of different radio sources around the sky. The radio noise from the receiver was stronger when the antenna was pointed at certain places on the sky. The strongest of these was the Sun, followed by a few supernova remnants like Cassiopeia A, and also the centre of our own galaxy. But there were a handful of sources from outside the Milky Way that were also known. This instrument, which was the 218-foot transit telescope, doesn't look much like a telescope, but it's a radio telescope. And this instrument detected the first of these, and that was actually the nearby large galaxy M31 in Andromeda, the Great Andromeda Galaxy. Now, by the late 1950s, Jodrell built a much larger radio telescope and was experimenting with combining the output of two radio telescopes together. The giant 250-foot Mark I telescope, as it was then, which was finished in 1957, and this is actually a picture in between the two surfaces of that telescope, and the original surface that we used in 1957 is this one down here with the numbers painted on it, and up above it there is the new surface. So 1957, this was completed, and as I said, around about that time we were actually trying what's called radio interferometry. Two telescopes spaced some considerable distance apart. Okay, so the Mark I telescope here is at Jodrell Bank, and there was a smaller 25-foot telescope, 10 times smaller than the other one, that was transported around the local and the not so local countryside, and its signals are transmitted back to Jodrell by a radio link. This picture is of the 25-foot at Pocklington in the Yorkshire Wells, about 132 kilometres from Jodrell. As I've said, a pair of telescopes like this is called an interferometer, and by varying the spacing of the telescopes, it's possible to obtain the angular size of the object that's being observed. And it soon became apparent that there were a number of radio sources that had very small angular sizes, almost point-like in fact, just like stars in the optical regime. And a lot of effort was put in to try and obtain accurate positions of these objects so that they could be matched with their optical counterparts, so we could find out what optical object was responsible for producing these radio waves. And finally, in 1960, one of these compact radio sources, dubbed 3C48, was actually tied down to an optical object. And here it is in the centre of the field, this one. Now, this is a picture from the original Palomar Sky Survey prints, and it's in the negative. And astronomers often use negative images like this because it's easy to pick out faint objects on them. Okay. So here we have the optical object associated with 3C48, and this sort of fuzzy blob here is a galaxy. Now this is actually the so-called red Sky Survey print. That is, it was taken through a red coloured filter. It's still in black and white, but it's taken through a red filter. So I want you to sit and watch this object as I display the blue print instead. That's the one taken through a blue filter. Okay, let's go back to the red and the blue. And you can see that the object is actually slightly brighter on the blue, indicating that it's bluish in colour. Now, note also that it actually looks like an ordinary faint star. And subsequently, the optical spectrum of this object was obtained, but it contained many unknown broad emission lines. That is, the lines were bright, not dark, as in most spectral lines from stars are. And, in fact, nobody was able to interpret that spectrum. Well, since no one knew what it was, it clearly required a name, and it was duly dubbed a quasi-stellar radio source, which, because that's a bit of a mouthful, was shortened to Quasar. So this was the first quasar to be detected. 2 years passed before another such compact radio source, this one called 3C273, and again here it is. And 3C273 was predicted to be occulted by the moon. That is, the moon was going to pass between the object and us, and in fact it was going to happen several times. And this actually enables the position of 3C273 to be determined quite accurately, because we know where the moon is. And it was then identified with the optical object shown here, and this is on the blue plate. And an optical spectrum of it was obtained, again, just like it was for 3C48. And that was done by Martin Schmidt using the 200-inch telescope at Mount Palomar, this telescope. Just to point out, this is the actual telescope, the mirror's down here, and this is all part of the mounting to hold the thing steady. And once again, this object showed the same odd emission lines. But Schmidt realised these are actually normal hydrogen lines, lines produced by hydrogen. But they were redshifted by a previously unheard of amount, almost 16%. And that gave a velocity for 3C273 of 47,000 kilometres per second away from us. And here's that spectrum. Here is the optical spectrum of 3C273. Okay, and we've marked some of the hydrogen lines here. Now normally they would be here. This is a comparison spectrum, but they've been shifted all the way down to here, red end, blue end. And of course they're also in emission, you'll note. And in fact, they then went back and re-examined the spectrum from 3C48, and that actually gave similar results now. But in this case, its recessional velocity was an incredible 37% of the speed of light. It was receding from us at an enormous rate. Here are some more quasar spectra compared with the normal spectrum at the top. And just to confuse you, these are the other way around from that one of spectrum of 3C273 I showed you. So here's a normal spectrum, and look at the hydrogen line here. and different ones, different redshifts. Redshift is denoted by Z here. So the hydrogen line shifted progressively to the right, so these objects going faster and faster and faster away from us. Now this obviously left a big problem. If you remember from the last talk, redshifts can indicate that the object is a long way off. If it was a galaxy with a big redshift, it would be a long way away from us due to the expansion of the universe. So if these redshifts were a result of the expansion of the universe, then it must mean that these objects are at absolutely enormous distances from us. And if they were at an enormous distance, then the amount of power that they must be emitting must be absolutely huge. But nobody had any idea of what could produce this sort of energy. For example, if we took 3C273 and moved it so it was only 33 light years away from us, it would actually shine as brightly in our sky as the sun, despite it being 2 million times further away. So it's kind of fortunate for us, it is in fact 2.4 billion light years away. The problem was made more difficult by the discovery that some quasars varied in brightness, with periods of order weeks or months, and that indicates that they must be less than a few light months in size, but nevertheless managed to put out more power than our own galaxy, which is over 100,000 light years across. Furthermore, as time went on, it became obvious that quasars aren't the only radio sources. I said our own galaxy is a radio emitter, but it's comparatively weak. There are some galaxies, however, that are strong radio emitters. Here's one that's close by. It's called Centaurus A, and this is a combined optical and radio image. Here's the optical, and this is the radio. And this sort of radio emission is fairly typical of radio galaxies. It tends to be in two distinct lobes, sort of here and here. As telescopes improved, it turned out that a jet or jets leading to the lobes, an example here, was pretty common as well. Now these had a similar, though somewhat less extreme problem to quasars, because the galaxies were much closer and don't require such prodigious amounts of power. Nobody was certain what the source of the energy was, especially when it's realised that the particles travelling in these jets were actually travelling at close to the speed of light, some things accelerating them by an enormous amount. In fact, for a while, colliding galaxies was a favourite, and this one was interpreted as an edge-on spiral sort of burrowing into an elliptical galaxy. And it's possible that actually that this is what's happening in this case, but that wasn't true for most radio galaxies. This wasn't all though. By the 1980s, astronomers had found quite a zoo of peculiar objects, safer galaxies with unusually bright nuclei and emission lines like this one. This is M106. Bielac objects, highly variable with featureless spectra. Starburst galaxies with lots of star formation going on. Quasars, there were radio quiet quasars, blazars, and normal, so-called normal radio galaxies. We still don't know what the source of the energy is. Now, of these starburst galaxies, like this one, this is M82, could be explained by having recently undergone a collision, which then provoked an increased rate of star formation, but this didn't necessarily work for the remainder of them. So what's going on? Well, come 1982, things came a little clearer. If you look very closely on the sky survey prints at the quasar 3C48, that first one I showed you, you can just see faint bits of fuzz surrounding it. And in that year, the astronomers Todd Borison and J.B. Oak managed to obtain a spectrum of this fuzz, and significantly they discovered that it was consistent with the spectrum of normal starlight at the quasar's redshift. In other words, the fuzz was actually a galaxy. So it looked like the quasar was embedded in a galaxy. things started to make sense. The quasar wasn't something totally different. It was a very bright and active galaxy nucleus. And soon other quasars were found to be in galaxies as well. Okay, so quasars are hyperactive galactic nuclei, but we're still left with the questions: what is the power source, and also why are all quasars a long way off? Let me read something to you. If the semi-diameter of a sphere of the same density with the Sun were to exceed that of the Sun in the proportion of 500 to 1, a body, falling from an infinite height towards it, would have acquired at its surface a greater velocity than that of light, and consequently, supposing light to be attracted by the same force in proportion to its vis inertia, with other bodies, all light emitted from such a body would be made to return towards it by its own proper gravity. Now, the English is slightly peculiar there, and that's because it was written by geologist John Mitchell to Henry Cavendish in 1783. And what Mitchell is proposing here is the concept of an object that is so dense and consequently has such a strong gravitational force at its surface that light itself can no longer escape from it. A few years later, Pierre-Simon Laplace promoted the same idea in the first 2 editions of his Exposition du Système du Monde, although he did drop it in later editions, probably because he thought it was too wild an idea. But these ideas were ignored through the next century because nobody understood how light could be influenced by gravity. But we, of course, know better. You will remember, I expect, Einstein's field equations from the cosmology lecture. Then we talked about how they were applied to the entire universe. However, they can be applied to smaller things. And shortly after Einstein published these, a physicist called Carl Schwarzschild found a solution that described the gravitational field of a point mass and a spherical mass. And the solution had the property that at some distance from the centre of the mass, something strange happened. And by the late 1950s, this had been interpreted as an event horizon, a sort of one-way boundary that things can only cross in one direction, inwards. And the radius at which this happens is now called the Schwarzschild radius, and it's given by this. Schwarzschild radius is 2 times the gravitational constant, familiar from Newton's law, times the mass of the object divided by the square of the speed of light. So it's actually a fairly simple expression. Now, the interesting thing to note is that the Schwarzschild radius is proportional to the mass of the object. So if the mass doubles, the radius doubles too. And for a normal sphere, if you double the mass by making it bigger, its radius would only increase by the cube root of 2, or 1.26. So something clearly weird is going on here. Some concrete examples. An object the mass of the Sun has a Schwarzschild radius of about 3 kilometres, whereas for an Earth mass it's about 9 millimetres, or say the size of a peanut, and for the observable universe it's around about 10 billion light years. Now, when we talked about stars in the Starlight lecture, I said that at the end of their lives, massive stars could collapse into very dense objects called neutron stars, as shown here. This one in the Crab Nebula. Now, in radio astronomy, these are first detected as pulsars. However, for very massive stars, more than about 3 times the mass of the Sun at this stage in their life, the quantum mechanical force that holds up a neutron star is no longer sufficient, and the star collapses inwards and onwards with nothing that is able to stop it. So briefly, the star collapses in on itself, folding space and time around it. Remember, mass and energy bend space-time. And in this case, it folds it so much around it that it becomes what was coined in the 1960s a black hole. That physical realisation of those solutions to Einstein's equations. Suppose we could travel closest to a black hole, what would we see? Well, apart from the dark disk of the hole itself, the most obvious thing will be the effect that it has on the sky behind it. The intense gravitational field of the hole bends and lenses light, a sort of extreme version of that bending of light that you saw on the eclipse of the sun as the stars get moved. And in this case, the light can go round the black hole more than once, and so you get multiple images. For example, the two bright stars in this picture, here and here, and also that star and that star's actually the same as that star's the same as that star. They've just got two images of each one. In fact, every star in the normal picture has at least one extra image, and near the black hole there's an image of the entire sky. Light from every direction, including behind you, has been bent round and funneled towards you, and the process is called gravitational lensing, and we can actually use it like a telescope. A better idea of what is going on can be seen if we move the black hole against the night sky. So here we go, hold on to your hats, and we're starting near the constellation of Orion, just down there at the bottom left. If we went closer to the black hole, it would appear to get bigger, and eventually it will fill our horizon. Now if we go closer still, what happens to it? Think of starting away from the Earth and coming closer and closer until you reach the Earth's surface. The Earth's horizon will eventually stop growing when it fills half of your vision, the remaining half being the sky. Well-behaved horizons do this. But this is not what happens when approaching a black hole, though. The horizon continues to grow as light is bent around behind you. It grows and grows, eating up the sky, which is compressed into a smaller and smaller disk centred directly behind you. Other odd things happen as well. Remember that you could think of gravity has been represented as a distortion in space-time. So for a very massive object like a black hole, we might have something like this. This is a sort of two-dimensional representation. Here's space-time, very massive object, and it bends it down quite significantly. And I want you to think about this circumference here. Now suppose we decide to measure the circumference of the circle around the black hole, okay, when we're in our orbit around it, say. Now normal circles have a circumference at 2 pi times their radius, but we find that it's a lot less than this, maybe twice as small. What's going on? Well, space is distorted. Your radius is now not that, it's this. So your radius is much bigger than the circumference implies. Space is distorted near the hole. Let's look at another property of black holes. To do this, well, imagine that somebody is sitting on a star as it's about to go supernova, and then ultimately collapse into a black hole. You'll have to sort of hang on tightly, but we're using our imagination here. And meanwhile, we'll stay out at a safe distance away and watch what happens. and we'll provide the chap on the star with a torch and ask him to flash every 1,000th of a second as the star collapses. So we'll turn the torch on and off rapidly every 1,000th of a second. This is an imaginary experiment, so he's able to do this. We'll receive the first flash and wait for the second one to arrive. Alright. And the person on the star does this 1,000th of a second after it did the first flash. But as the star collapses, space-time is stretching around that star, and so we receive the flash slightly more than 1,000th of a second after the first, because the light has to travel a little bit further than it did for the first one. Let's put some concrete figures on this and assume that the star takes 15 seconds, as measured by the person sitting on it, to collapse to a black hole. So we receive his 10-second flash. So he sends out at 10 seconds, actually 14 seconds after we receive the first one. And you receive the 11-second flash 16 seconds later, the 13-second flash 19 seconds. And the flash 1,000th of a second before the black hole forms, it actually takes it 137 seconds to get to us. And the 15-second flash, the one that he sends out just as the star forms a black hole, never reaches us. Space around the black hole is now stretching at the speed of light, so the flash never reaches us. Now actually, the light from the torch will be being redshifted more and more and more as the star collapses, and we'll be left with a very faint, very red image of the person sitting on the surface of our star and the torch at the moment just before the black hole formed, and this will stay more or less forever. Now, the good news is, at least for the person sitting on the star, as he will probably not see or experience anything unusual, apart from it being a bit hot and uncomfortable. So he won't see anything unusual when the black hole forms. As far as he is concerned, nothing out of the ordinary happens, at least until he gets close to the singularity at the centre. And the singularity is the very centre of the black hole. Now, because near there, unfortunately for him, the gravitational tidal forces will result in a fate known as spaghettification. And the reason is that the gravity, suppose he's going down feet first, that the gravity at his feet is now enormously higher than the gravity at his head, and so it gets stretched. Now, this seems to be an appropriate point to look at the inside of a black hole. The event horizon, the point of no return, is at the Schwarzschild radius. Okay, this green one here. So it's at the Schwarzschild radius away from the singularity, and at it, space and time are effectively swapped. The person sitting on the star's options are now very limited. All matter is going to end up at the singularity. 1.5 Schwarzschild radii away from there, outside the event horizon, is what's called the photon sphere. And there are in fact no stable orbits within this. Anything between here and the event horizon must either fall into the black hole or escape, but it can't stay there without expending some power. Now actually, this is for a black hole that doesn't rotate. It's likely, however, that our collapsed star will be rotating. Pulsars, for example, rotate very fast. So for this, things are somewhat more complicated. Rotating black holes are sometimes called Kerr black holes, after the New Zealand mathematician who discovered the relevant exact analytic solution to the field equations in 1963. Like non-rotating black holes, Kerr black holes have a photon sphere. Well, actually they have two. Which one is relevant depends on which way around the hole you're going. But I haven't shown those to avoid cluttering up the diagram. Apart from those, going from the outside in, we have what's called the Ergosphere. And in this region it's impossible to stand still because the black hole is actually dragging space-time around with it. It's called frame dragging. And as for a stationary black hole, space and time are interchanged at the outer horizon. This one. But they're swapped again at the second inner one, so rotating black holes have two horizons, one inside the other. So you now have a few more options once you're inside here, because you're now in relatively normal space-time. You could actually wander around inside it and avoid the singularity. Speaking of which, the singularity is different to that inside a stationary black hole. It's actually a circle, it's a ring, it's of zero thickness, and the singularity actually repulses rather than attracts unless you approach it exactly on its equator. So you could sort of hang around in there for quite some time. Now, this is all very theoretical. Is there any observational evidence that black holes actually exist? Well, yes. Initially, at least, we can infer their existence. Here are some orbits of some stars at the centre of our own Milky Way galaxy. A number of stars all labelled S something, and these are their orbits. Okay, and the centre of our galaxy is here. And we can use these orbits to infer the properties of the object that they're orbiting around. The star S2, for example, this one here, has an orbital period of 15.2 years, and it approaches to within 17 light hours of the central object. That's about 120 times the distance of the Earth from the Sun. And from that orbit we can calculate the mass of the central object, and it's about 4 million solar masses. And we also know that it must have a radius less than 17 light hours, because this object, that's as close as this object gets. And recent observations indicate, in fact, that it's no more than 6¼ light hours, about the diameter of the orbit of Uranus. And in fact, an object that small, containing 4 million solar masses, has got to be a black hole. Now, the black hole at the centre of our own galaxy is pretty quiescent. This is an image of the centre of our own galaxy. And it has an occasional outburst, but not much. What causes an outburst? Well, basically, it's matter spiralling round and into the black hole. As it spirals in, going faster and faster, it sort of rubs against itself, friction, and generates a lot of heat and light. So if the Milky Way has a black hole at its centre, do other galaxies? Well, briefly, the answer is yes. Let's take a look at M31, the Andromeda Galaxy, our closest large external galaxy. And this is a picture taken by the Chandra X-ray Observatory at the centre of that galaxy. And X-rays show matter that is very hot. And the yellow-coloured objects here are thought to be X-ray binary stars. But what I'm interested in is that blue one in the middle. And the blue-coloured object is coincident with the position of a black hole inferred from star motions. And this black hole is reckoned to be 100 to 200 million solar masses, 25 to 50 times that of the one at the centre of our Milky Way. What about other galaxies? Well, this is the Coma cluster of galaxies. The bright one on the left here is called NGC 4889, and it contains the largest black hole so far detected in an otherwise normal galaxy. And this one weighs in at an estimated 21 billion solar masses, over 5,000 times the Milky Way's black hole. And the most massive one detected so far is in a quasar SDSS J103225.31 plus 514251.0, I'll test you on this later, which weighs in at over 33 billion solar masses. So there's some really giant black holes out there. Another one, Hercules A. This is a strong radio source. And again, this is a mix of optical and radio picture. Here's the radio emission, and down here, and then the optical here, plus all these stars and other galaxies. And the black hole at the centre of this galaxy is about 4 billion solar masses. And these plasma jets, by the way, are about 1 million light years long each. Now, there are obviously a different class of black holes than those caused by a large star collapsing. So did these form first, before galaxies, or did they form after? Well, we don't really know. So conveniently sidestepping that question, let's go back to the question I asked before starting to talk about black holes. What powers the radio source in this case? Or in general, the quasars I discussed earlier on. Well, now we have a probable answer, the black hole at the centre. Now at first you might think that an object well known for not letting out any light might be a bad choice for a source of vast amounts of energy. But what would happen if lots of matter was spiralling into the hole? The galaxy M87 has a large black hole of 6.5 billion solar masses, which is actually directly imaged by the Event Horizon Telescope. This is a radio image, and the results are released in April 2019. And what you see here is light from what's called the accretion disk. That is material spiralling down into the black hole. The event horizon itself is actually 2.5 times smaller than this sort of dark shadow at the centre. This one. And that's because of the gravitational bending of light. It's about 40 billion kilometres across, so it's about 10 times the distance to Neptune from the Sun. Now, as material in the accretion disk spirals down into the black hole, the large gravitational gradient results in intense frictional heating. I've mentioned this before, and close to the event horizon, the matter is actually hot enough to emit X-rays. And this process is very efficient. It can convert about 10% of the mass of an object into energy, as opposed to, say, only about 0.5% for nuclear fusion, the sort of process that goes on inside our own sun and most normal stars. This is actually the jet in that same galaxy M87 as seen by the Hubble Space Telescope, and the black hole is in the bright spot at the top left of the picture. So it's in here. But it's too small to see in this image. Observations show that the particles in this jet are moving at relativistic speeds, that is, they're comparable with the speed of light. So what can do that? Well, the favoured theory is that the twisting of magnetic fields in that accretion disk, the sort of stuff spiralling around and into the black hole, as a result of the spin of the black hole, collimates the outflow of material along the rotational axis of the black hole. And the material in the jets can be possibly accelerated by the tightening of the field lines. So we have these twisted magnetic field lines around the jet, and the material is pushed out between those. And there's your accretion disk, and you have a black hole right at the middle. An alternative, though, is by the Penrose mechanism. So let's go back to a rotating black hole and remember the ergosphere, this bit. That's the region of frame dragging, where space-time is dragged around by the black hole, by the rotation of the black hole. And in fact, it's possible to extract energy from it in that way and transfer it to particle energy and momentum. The black hole slowly slows down as a result. And in fact, it's possible to extract up to 29% of the black hole's energy in this way. And it's the most efficient energy extraction process known. It's 60 times more efficient than the nuclear fusion reactions that power stars. So there you are, that's the answer to all our energy needs. All we need is a sufficiently large black hole. So now we have an idea of what powers active galaxies and quasars. This is the quasar 3C273, showing on the right its host galaxy. Okay, we blocked out the light from the quasar so you can see it. So here's the fuzz of the surrounding galaxy. Why are quasars all distant from us? Well, black holes appear to be more active in the past, having more material available to swallow, and so possibly then we only see quasars in the past and a long way off. Different sorts of active galaxies and quasars, as seen by us, can be explained by considering how the jets are aligned with respect to us. A jet pointing directly at us, directly towards us for example, will look very different from one transverse to our line of sight. Now the jets can actually have quite an impact on their galaxy. This is a combined optical, infrared, X-ray and radio image of the galaxy M106. It's relatively close, it's about 23 million light years away. And notice these extra rather peculiar arms, these sort of purple things. And studies suggest that these are heated gas being ejected from the galaxy, and the heating is being produced by shock waves generated by the jets from the central black hole, and those jets strike the surrounding medium and heat it up, and then the gas is escaping from the galaxy. In fact, it's estimated that this galaxy will have lost all of its gas in about another 300 million years, which is a really short time. And if you lose all your gas, then you have nothing left to form new stars out of. So, does this mean that we now understand everything? Well, no. The event horizon and the singularity of black holes is where relativity and quantum mechanics collide. But these two great theories are inconsistent with each other. They have different conceptions of space-time, and lacking such a theory of so-called quantum gravity means that we don't have an understanding of places like these, and that includes, incidentally, the early fractions of a second after the Big Bang. Now, black holes are massive objects that distort space-time. If they move or change, then they can distort space-time in such ways to produce waves, gravitational waves. Think of throwing a stone into a pond, you get ripples. Gravitational ripples in space-time, though, are very difficult to detect because they are so weak. Gravitational waves have a very small amplitude. The equivalent strain in space-time is 10 to the minus 22. So over the 4-kilometre arm length of this instrument, which is the Hanford detector of LIGO, the change in arm length as a gravitational wave passes it is about 10 to the minus 18, or 1,000th the diameter of a proton, 1,000th diameter of a hydrogen atom nucleus. Now this is a form of Michelson interferometer, a bit like the Michelson-Morley experiment they used to show that the Earth wasn't really moving through the ether. And here's a diagram of one of the advanced LIGO detectors. When a gravitational wave passes through the instrument, it affects the length of these two big long arms. They're each 4 kilometres long. Okay, and there's mirrors here which bounce light in between them, and these are actually shifted. These are moved relative to each other, and then the change can be detected down here. So it moves these sort of test masses at the end with mirrors attached. And here is the first detection of a gravitational wave. A good way of generating gravitational waves is for two black holes to get close enough to merge, and when this generates gravitational waves as they spiral in towards each other. And in fact, in September 2015, the first signal from such a thing was detected. And here's a diagram from the paper, and you can see the effective change, the strain, the change in those arm lengths as the wave passes through. And they've actually got two detectors. They've got one at Hanford and they've got another at Livingston in Louisiana, and you can see that the two match with a slight time delay between them, consistent with how far apart they are. The gravitational waves travel at the speed of light. And in fact, the best fit to this data is two black holes with masses of 29 and 36 times that of our Sun merging, and they're thought to be about 1.3 billion light years away. So these ultimately merge and form a single black hole, which is 62 solar masses, which is somewhat less than 29 plus 36. So 3 solar masses of energy were emitted in fractions of a second into those gravitational waves, 50 times the power of all the stars in the observable universe. Many more have been detected since. The second one detected was in December 2015, and that was 2 smaller black holes merging, and in January the following year a third, and August the following year, 4th, which was also observed by the Virgo detector in Italy, and many more have been made since. And in 2017, 17th of August, LIGO detected its first merger of 2 neutron stars in the galaxy NGC 4993, shown here. And the event was also detected in the optical and as a gamma ray burst. And here it is. Sudden brightening. Now, incidentally, these observations, together with modelling, suggest that the debris cloud around the merger contains about 200 Earth masses of freshly minted gold and 500 Earth masses of platinum. So it's possible that all of the gold in the universe, as well as half of the other elements heavier than iron, actually comes from mergers like this, from neutron stars merging. Have any of you got a gold ring on? Well, look at it now and think about where it might have come from. The actual detection of gravitational waves has given a boost to the planned spaceborne LISA mission. And again, this uses lasers between test masses, but this time with 3 arms, each 2.5 million kilometres long, as opposed to 4 kilometres, and needless to say, is based in space. A technology test mission was launched in December 2015 and has been very successful, exceeding its design goals, and the mission was concluded at the end of June in 2017. Now, LISA will be sensitive to lower frequency waves than LIGO. Binary stars in our own galaxy, supermassive black holes and other high mass objects. Also, speculatively, signals from cosmic strings and primordial gravitational waves generated during cosmological inflation. And the latter would let us see almost right back to the Big Bang, unlike electromagnetic radiation, which is limited to about 300,000 years or so afterwards. Well, the planned launch for this is expected to be about 2034. So you'll just have to hold in your excitement. Well, there we have it. This is Cygnus A. I've tried to give you a bit of a flavour of what astronomers and physicists know, or think that we know, and what we don't know, or think that we don't. In fact, as you may have noticed, there's plenty that we don't know or understand, which is all very encouraging, because imagine how dull it would be if we did. Well, I hope you found these talks interesting and that you've got something out of them. Maybe you can now see what it is that drives astronomers to try and understand everything that's out there. Even if we cannot hope to, it's lots of fun trying. Keep safe, and goodbye for now. Goodbye.